All right, y'all, it's Barry. I'm here today to talk about our last unit in AP Physics 1. It's electricity time, so we're going to get right into it and talk about the big ideas that come with electricity. So we have 1, 2, 3, 4, 5, everything but 6. So all of our big ideas except for waves are going to be present in this unit. We've gone through these a lot and seen them in every unit at this point, so I'm going to save us a minute because we got a lot of slides to get to, but you can see them all there. Keep them in mind. We will hit them again at the very end as always. All right, the first thing we got to start with when we talk about electricity is charge. Something that you probably know from chemistry, but to reiterate, charge is an uneven accumulation of protons or electrons. More protons is a positive charge, more electrons is a negative charge. A common misconception is that having a positive charge means there's only protons, and that's not the case. It just means there's more protons than electrons. 10 of one and 5 in the other still means a positive and an accumulation of the 10. So if it's 10 positives, or 10 protons, you'd have a positive charge. 10 electrons, you'd have your negative charge. The amount of charge that's there is going to be measured in coulombs. And we see here the units that we're going to use for that, they are very big because protons and electrons are very small. So hopefully that makes sense. But the charge of protons and electrons, you see the individual ones are very small right here. And thus we need the equivalent number of that individual charge in actual protons to make 1 coulomb. So because a proton has a charge of 1.6 times 10 to the negative 19 coulombs, it takes 1.6 times 10 to the 19 protons to make 1 coulomb. This is available on your equation sheet, not something you need to memorize, but I want to make sure we hit it so you know what we're looking at for units. All right, and a quick reminder here that like charges repel. So we see our first two there, 2 positives, 2 negatives, they're going to repel each other, but at the end, they're together when they are opposite charges. So opposite charges will attract. This holds true for objects that are holding a charge because of a collection of protons or electrons. So if they have an excess of them, this is what we're going to be looking at here. Now, objects likely to hold an excess of protons or electrons are known as conductors. And these contain free charges that move easily. So it easily allows for the flow of electrons, and we're going to look more specifically at electrons and that flow there of electrons because we're talking about electricity, but really they can hold the charge of either one pretty well. Conductors are more likely to generate electric fields, and that is to say they're going to bring in excess protons or electrons that are near them and allow that to build up in a field around it. We're actually going to look at what's really just our second field that we've covered in AP Physics 1 beyond a gravitational field. We're going to look at an electrostatic field coming up here in a minute. But you see there, electrostatic equilibrium. This is a state where all the free charges move outward from the conductor. And that is to say, when we have an equilibrium state, we always have that zero state. So in those cases there, we're going to be getting rid of, if we have full electrostatic equilibrium, we're going to have an equal amount of electrons and protons or no excess. And so we're going to have a charge of 0 overall. Now, when we get to insulators, hold electrons within their orbital bonds. They don't really allow them to move freely, and there's not going to be really any excess buildup around an insulator. Okay, and again, we see some of the objects to go back real quick. Conductors, most conductors are going to be metals. It's really what it comes down to. So metallic objects are the best conductors, and insulators are going to be other materials that are very low in the properties of metal objects. Things like you see rubber, glass, ceramics, plastics. And the bottom here, you actually see a setup of some transformers that help deliver electricity to your home. Well, there's ceramic pieces within that. You probably didn't realize that because you probably haven't touched them, and you shouldn't touch them because they're very dangerous. But they have ceramic pieces in there that keep the correct parts insulated and keep there from being electrical fires, which is a good thing. But you see wool and wood, some of the most basic ones over there on the right as well. Now, there are a few ways that we can charge these objects to build up this excess. One of them is just charging by friction. And you see here a fur object being rubbed on a rubber object, and it causes a transfer here of these different materials. But an easier way to think about this is if you have a carpet at home, if you've walked across the carpet with socks on, and then you've touched a doorknob. And what you've done is through charging a friction, through your socks moving against the floor there, that frictional charging, you have built up a charge on yourself, and it discharges when you touch that metal object, when you touch that conductor. This also happens when it's cold outside and you touch a doorknob to your car. Maybe you've been shocked from something like that. That is charging through friction. So the total charge is going to it's going to move from one object to the other. If you could count all of those little positives and negatives that you see down here in this diagram, then you would be able to count the same number of negatives as positives. We're not creating anything here. Matter cannot be created or destroyed. We're just transferring these different parts from one object to another. And so along those lines, since conductors are more capable of transferring, we have another way that we can cause these charges to build up, and it's known as conduction. And really what we've got then is we take two conductors, one with a charge, one without, we touch them together, and the charge is transferred through conduction between conductors. And that's all it comes down to right there. You see the diagram there that shows that, okay? And this shows more specifically a charge being transferred to an electroscope that causes then an equal distribution overall, and it's a little more in depth, but as a general idea, really, we're just moving charges from conductors, right? The last one's a little more complicated. It's known as induction, right? And this one is more like a little bit of a trick, I'll say. But induction is charging a neutral system because, again, we're just kind of being tricky. We're using our properties here. So what we've got here on the left is two uncharged objects, and they are touching. They are both conductors. You see two metal spheres there at the bottom. If we were to take a balloon, and if you could take like a balloon, just blow it up, rub it on your hair, rub it on a piece of cloth, something like that, it will build up a charge around it, okay? So if we were to do that, we could get a negative charge on this balloon. Well, since these are conductors, they allow the items within them to move more freely. And so if we took this negative charge here, well, if we go back up real quick, we said, okay, negatives repel, but to a negative, a positive will attract, right? Well, if that is the case, then we put this negative charge here near these two neutrally charged spheres. The positives will move, the positives that can move freely will move freely towards that negative because opposites attract. The negatives that can move freely will move away from it because likes repel. And then we take these two objects and we separate them just by pulling them apart right here. And with all the negatives moved over to this side, we have a negatively charged object. And then if we move the balloon away, we end up with a positively charged object on this side. Now, one important piece to this, you cannot actually touch the balloon to the sphere, because then you will have an actual transfer here of these and potentially cause a neutral state because the charges will cancel each other out. But if you do this, then we have what's known as charging through induction. We haven't actually moved anything into or out of this system. We've just moved the two parts between the system and distributed them differently. And note again, 5 positives, 5 negatives, equal movement here overall. Okay? Now, what you've built up then around a sphere like this would be known as an electric field. Okay, an electric field is just to say we've built up some amount of charge in the space surrounding an object. Right? This is an area in which non-contact forces are generated because these charges have built up. And the closer the opposite charges are, the stronger the force will be. Okay? So if we have a positive electric field, positives typically move outwards, is how we consider them to move, and negatives are considered to move inwards. This is kind of like when we looked at clockwise and counterclockwise. It's just our way of defining direction, positives being outwards, negatives being inwards. If we were to move these two close to each other, they would attract because this one would push out, this one would pull in, and they would go towards each other. But if this was negative and pulling inwards, then we would have that repelling, or I guess it's easier to see, I guess if we said this one was positive and pushing outwards, this pushes out, this pushes out, you see why they repel against each other, okay? And we can see that here in the case of the opposite charges and how they're attracting towards each other. So this is an electric field interaction. We have the positive that was shown here and the negative that's shown here interacting with each other. And so we're going to have a force that's strongest where the arrows are closest together and weakest where they're furthest apart. And hopefully that makes sense, because really here in the middle, you are seeing that you are close to both charges, essentially equally if you're right in the middle there. And so you're going to have interactions with both of them, whereas if you're way out here in the top corner up there, or even like way down here, or wherever you are while you're watching this, you're much, much further away, and thus the field's going to be much weaker. And this is why you aren't shocked all the time by everything whenever you pick up any charge. It's because it's about the strength of the field also. It depends on how close you are to the material actually causing the charge. So if you only build up a little bit of friction as you walk around, then you're less likely to have a field built up around you to discharge. And this is why you only get shocked typically in the winter. It's because it's drier out and it allows that field to build up much easier. All right, forces within the fields. So we've talked about things like a gravitational field, and then there's a force of gravity on one object. Well, that same idea is going to hold true here, because again, it's a field. It's a force generated by the field that surrounds it. Okay, so there's an electric force that's going to be present, and that's going to be that actual force of attraction between these opposite charges or repulsion between these like charges. So we have our electric fields built up, but they're going to cause on, let's say, an individual particle that might be near the field, they're going to charge some sort or cause some sort of force to happen there. All right, we can measure the strength of the electric fields here by using these equations, and this is something we're going to go much more in depth into, and we'll be able to measure the actual force coming up here with Coulomb's law in just a minute as well. Okay, but the electric field strength could be said to be the force generated divided by the charge that the force is acting on. A good way to think about this is gravitational field, right, would be generating something along the lines of a gravitational force on a mass. We're just looking at charge now instead of mass. It is still going to have something to do with the distance from it, because as you get further and further away from a gravitational center, that force of gravity gets less. Same thing is going to be true here as you get force further and further away from an electrical force generation or an electrical field generation. The electrical force is going to be less and less as well. So a couple examples of electric fields, because I think this is something kind of hard to visualize. You've probably been shocked because you touched something metal before, but it's not like you see that happening, and you don't see it nearly as regularly as you see gravity. Some things you might have seen before would be, okay, we've got this rubber rod here that's charged. That's something that would be kind of a classic lab. So if we do labs, we'll be able to show you that. But in an old tube TV, not a flat screen, but the old tube TVs that you've seen before, you turn it on and you start to hear it, right? It does the buzzing sound. That's because it actually creates an electrical field inside of it, and it bombards the screen front with these pieces from the electrical field, and that's where the image comes from. Okay, and so in a TV picture tube, we would have a value for the electrical field that's inside there of about 1.1 times 10 to the 5th newtons per coulomb. Okay, and that's how we're going to measure that, is the force, the newtons, the number of newtons, the amount of force per coulomb that's generated by the electrical field. To show you a little bit more, that's not quite enough then to make a spark in the air like if you were to touch a doorknob. All right, and needed to make a spark in the air, it's going to be about 3 times 10 to the 6th newtons per coulomb. And then you get down here, an electron orbiting in a hydrogen atom, that's got a really high electric field there. And that's really good, because if atoms started falling apart, we'd have some big problems here, right? So it's a good thing that electrons aren't falling off atoms, because, well, you wouldn't be able to watch this anyway, so it wouldn't matter. All right, an example down here. We have an electric field. It's to be measured using a positive test charge of 4 times 10 to the negative 5th coulombs. What that means is we're putting this little charge out there, and we're going to see what happens to that charge in order to determine how strong the field is. And so the test charge then experiences a force of 0.6 newtons acting on it. If we want to know the magnitude of the electric field, we would say then E equals F over Q. Sorry for the weird formatting. I'm not sure why that just happened. But we have 0.6 newtons then divided by this 4 times 10 to the negative 5th charge. And that makes sense. These charges are going to be very, very small, which is why these numbers seem very big. But that gives us then 1.5 times 10 to the 4th newtons per coulomb. This is about in the range of the values that you might see on some of the problems in class. So a reminder then, typically if you were in person, I would have you fill these in. I'd show them once you see what's going on, but we've already gotten the answers there, so there you go. We know that likes attract and opposites repel. All right, so Coulomb's law. This is going to explain how we can actually gather a piece of data to determine the force acting between these two charges that might be existing in space somewhere. Okay, this is going to look very, very, very much like your gravitational equation, because it is a force generated by a field. Okay, so if you remember, gravitation was F capital G, excuse me, the force of gravitation equals big G, mass 1, mass 2, divided by the radius squared. All we're doing instead of that is looking at the charge of an object as opposed to the mass of an object. And so we've changed mass to charge, and boom, that's it. Now there is a different constant. You see here we have Coulomb's constant, right? That's going to be 9 times 10 to the 9th Newton meters squared divided by Coulomb squared. And again, units and constants are there to make sure the equations work. That's why constants exist. So we're not going to worry too much about the crazy units associated with that. But this will give us a force in Newton. So this Fe, that is the electrical force, that's there because there's an electric field present. Would be the electric force between these two charges. If these were opposite charges, a positive and a negative, then the force would be pulling them together towards the center. If these were both negative charges, then the force would be acting outwards, away from each other, and they'd be repelling. Again, with that really just being positive and negative, just being direction, as I've said many times in class, and as I'm sure you all know by now. So something to remember, charges will be positive or negative, and that only tells you the direction. So state it again right there. All right, a quick example here. We have two charges. They're fixed on the x-axis. We have a negative 4 Coulomb charge at negative 2 meters, a 3 Coulomb charge at 4 meters. We want to find the force on one and the force on the other. And then what if the same charges are moved so that they are 3 meters apart? So again, the force, first of all, on one, we would find just K, and then the two charges, so K being our constant, 9 times 10 to the 9th Newton meter squared divided by Coulomb squared, are two charges in coulombs, and then the distance. And they are going to be equal and opposite in direction. So it doesn't matter that one is negative 4 coulombs and one is 3 coulombs. They will interact the same way. All we would really do then is change the 3 here and 4 there, and we're going to get the same value. So the force acting on each will be the same. Now, if we change the radius and we cut it to half the radius, that would end up making an overall change there of 4 times greater as far as the actual force, and this would then be the force acting on these two charges. All right? So that's going to kind of sum up our electrostatics and looking at electric fields. Obviously, we'll do much more with that in class. But now we need to start looking at what happens when we no longer have this buildup of charge, of this excess of charge that's just floating in space as a field. What happens when it comes together and starts moving together? When that's the case, we have something known as an electric current. So this is the net movement of electric charges in some single direction. Now, this is not going to happen in space. Okay, it's not going to happen out in space like we would have for these fields, where really all of a sudden you have them all moving in one direction. The closest thing that we could see to something like that would be like a lightning strike, but that's really just an electrostatic discharge. That's not really the same thing here as a current. Okay, this is going to be something largely generated by humans to transfer electricity. That's basically what we're talking about here. An electric current is electricity transferring. It's measured in amps or amperes, and really you're just going to see capital A. Probably refer to it more often as amps than amperes, but just so you know what both are. And it's the flow through a closed path called a circuit. Okay, so if we have a wire that's a closed path, we can have electricity flowing through it. All right, so that's the first thing there. That flow is just known as the current. Now, electric current and voltage. So a voltage difference, and you're going to see a number of names for this. So I want to make sure to mention them all so that you realize that they're all the same thing. A voltage difference, or potential difference, or just voltage. They all mean the same thing. This is the ability to move an electric charge through a resistance. Okay? And I'll refer to this typically as the push. Okay, this is what pushes the current. The current is there and it exists, and it's that buildup of charge, but it has to be that flow of charge, and what causes it to flow is this push that comes from voltage. Okay, so it's measured in volts, and that's why we'll more often than not refer to it as voltage, because if something's measured in volts, why would we call it potential difference, right? But whatever, someone smarter than me came up with these names. Increasing the voltage difference in a circuit will cause more current to flow. It's more push. Okay, so I could have the same amount of current, but if I have a higher voltage, it's going to give it more of a push and then thus cause more of it to move by. And we'll get into some labs that'll show you how all this works. But in a DC circuit, in a direct current circuit, which is what we're going to deal with here in AP Physics 1, we're not going to have any alternating current, just direct current. Voltage is produced by a battery and gives the current that push that it needs. Okay, so to look a little bit about kind of how that works. A DC circuit, again, the voltage source for them is going to be simply a battery, and it's a device that stores chemical energy and makes it available as electrical energy. So the direct correlation between chemical energy and electrical energy is caused because of, or creates, a direct current. This is not what is in your outlet, in your wall. That's an alternating current, and that comes because of a turbine. That's a little bit of a different setup, and that's something we can talk about later, or that's more of an AP Physics 2 topic, okay? Here we're really going to be dealing with batteries and direct current only. Now, the point of having a current with a voltage push through a circuit is because of resistance. And that seems odd because I'm saying, okay, well, we want it to be resisted, but you do, because the resistance and what is a resistor is something that, did I really spell that wrong? Excuse me, is something that, that uses up some of this current. All right. And if we're not plugging something in, then why are we bothering to do this, right? If we're not running a light, if we're not running a fan, if we're not getting your computer to light up and get moving, there's no point in this whole process. So resistance is the tendency of a material to oppose the flow of electrons. And that is also to say to use that flow of electrons as they get there. It changes electrical energy into thermal energy and light. And insulators have more resistance than conductors because they insulate, and so they don't really allow, they have a high amount of resistance than associated with them. Also, thinner wires, longer wires, and hotter wires. So thinner, smaller cross-sectional area, longer, they go a longer distance, so the longer the current has to travel, and hotter, higher temperature, higher thermodynamic energy, will all have more resistance. And this is because it doesn't allow the electrons, the flow there, that current flow, to move through it as freely, and thus you get this more resistance associated with it. All right. Now, if we actually look in wires, because you're not having any sort of circuit really without wires that attach the different pieces to it, whether it be what you plug into the wall, again being alternating current, or the pieces within an actual electrical device, you're going to have little wired pieces in everything really. So lots of factors are going to affect how the current flows through a wire, and we see those again right there. But we can actually calculate the resistance in wires based on, and R is going to be our resistance overall. R is the resistance that we're looking at here, based on the resistivity, and that's going to be based on the actual material, right? Copper is what we typically use, as opposed to, let's say, gold, not because one is more rare, well, partially because one is more rare than the other and thus worth more, but also because one allows for flow better than the other, okay? So that's why we do that. It's going to be based on the length and then the cross-sectional area also. And those are things that we've covered a little bit. This is not an equation. It's on your equation sheet for AP Physics 1. So if you were to be given a problem where you'd have to solve for this, they would give you this equation and make sure that you had that. I'll show you the actual resistivity of some common materials. You see things over here, metals. Metals are going to be the low ones. And the -8s and -7s that you see here in this left column, they're going to have the lowest resistivity. And that's what we want when we want to have a current flow through something. We want it to be as little resistance as possible. And you see copper is actually the second lowest one. Silver is actually has a lower resistivity, which means it will allow current to flow through it better. We don't use silver because it's rarer and it costs more. And if you look at the difference there, it's almost nothing, right? So it's not worth multiplying the cost of these materials that you need to build with by the factor that goes from copper to silver just for this tiny little increase in resistivity that you've got there. Now, things like platinum, I mean, obviously this being more expensive and having a lower resistivity, I mean, it's just not worth it in that case, right? And then we get over here on this other side, and we get to things like coal, silicone, human skin. If you look there, I mean, that's a big one. These are -8s, 10 to the -8. This is 10 to the 5th. And that's good because you don't want to be a conductor. That would be very bad in a world where we're surrounded by electricity. You would get sparked all the time and shocked all the time, and it would potentially do much more damage to your organs and the rest of your body if you had a lower resistivity. So it's good that you are resistant to a current. Glass then going up from there, rubber and sulfur and quartz, all having very high resistivities, which is to say they don't let electricity really flow through them almost at all. And that's why we wrap all of our cords in rubber. As we've got this copper here, right, that has a low resistivity, it allows that flow through it really easily. And then when we put a high resistivity object like rubber around it, then it's going to make sure that when you grab a wire or you unplug something, you're not getting shocked. It's protecting you from that current that's moving through the middle there. Okay. Now, we've gone through these things. We've gone through the voltage that gives the push to the current. And then there's the resistivity associated with that. Well, now we need to see how those things relate to each other and how they work in conjunction here to make circuits happen and to make electricity something that's useful to us. So in order to do that, we need to look at Ohm's law. And luckily for us, it's really, really simple, right? There's not the squared values, the factors that go in here of 1/2 or times 2 or whatever else. There's no constants. It's just Ohm's law is the voltage, V, equals the current, I, times the resistance, R. And that's it, right? Again, current measured in amps, A, voltage measured in volts, and the resistance of an object is going to be measured in ohms. And that's an omega, a capital O in the Greek alphabet. Okay, so resistance in ohms. And a quick example of how this could work here. We have an iron. It has a resistance of 9.6 ohms, and it's plugged into an electrical outlet with a voltage difference, all right, with a voltage supplied to it of 120 volts. And that's theoretically what the outlets in your home are. So if you were to plug an iron into the wall, basically is what we're saying here. Now, it's probably not the most accurate resistance, and it's not actually 120 volts in your wall. It's more like 114, but whatever. That's not as important here as seeing how all this would work. The current flowing through the iron then we're just plugging our numbers in for V equals IR, right? And we would get 12.5 amps of current. And it's good that that number 9.6 isn't right, because 12.5 amps of current is enough to kill you pretty quickly. Something pretty interesting, I tell this every year when we go through these notes, is that the current is actually much more dangerous to your body than the voltage. The voltage, remember, is the push. If you have a high voltage and a low current, that's going to push a little bit of electricity through your body really quickly. And for the most part, if there's only a little bit of electricity, it's not going to do much damage. But remember, that current is the flow. And so if you have a flow, a high current, then it's going to be a lot more of this electricity moving through your body. And that's what can really do damage. The reason that they say high voltage when they put like a warning sign on something is because it's a lot easier, because the numbers associated with voltage are much higher. If you see two signs that would both be correct on a transformer station that it's warning you to stay away, one says warning 50,000 volts, the other says warning 8 amps. Which one sounds scarier? That 50,000 number seems much scarier, especially to people that don't know what they're doing, right? That don't really understand what the difference between these voltage and currents are. Well, I would be much more scared of 8 to 10 to 12 amps than I would be of 50,000 volts. But most people aren't. Most people are more scared of the bigger number, and that's why they use the bigger number for those warning signs. Now, speaking of which, we do all this to generate electrical power, right? This is power generated by electricity, and it's similar to the power discussed earlier. It's measured in watts, okay? And that's important. So this is measured in watts. So electrical power, it's what we use to power objects. It's determined by the current present and the voltage produced. So current being that amount of electricity, voltage being how quickly it's being pushed. So hopefully that makes sense. That is how we can determine how much electrical power is going into something. And you see down here how that works. Now, because we know that Ohm's law is V equals IR, we can rearrange this and plug this in a couple different ways to this P, electrical power, equals VI equation, and get some different ways to calculate this overall. Okay, so if we did some substitution, we'd have some other ways to calculate that. So I wanted to show you all the different ways that you could calculate electric power. Now, beyond that, electrical companies, they care more when they charge you for the amount of electricity that you have about what we refer to typically as electrical energy. They don't really care how much you're drawing by itself. Okay, you could power something that requires a ton of electrical power here. I just used power twice, and that's a poor description, so I apologize. But let's say you have a huge big screen TV with all the surround sound and all that stuff set up in one home, and in the other home you're powering a light bulb, and that's it. Okay, well, if I turn that TV on, if I watch it for 2 minutes and I turn it off, and I don't turn it back on for a year, or if I power that light bulb for the entire year, I can't just say, well, one pulled more power and so it had to cost more to run. It's also about how long it runs for. Okay, so electrical energy companies charge using something known as kilowatt hours. And note that that's kilowatts, so thousands of watts in power, times the number of hours that you run something for. And you see that down here in the bottom right. Electrical energy is P, so the power of the electrical appliance, in kilowatts, times the time that you're consuming this electricity in hours. That is a weird unit, and it's done more to make the numbers more manageable when you are actually charging people for using electricity than it is for physics purposes. But it's a very common application of this stuff, so I want to make sure you're understanding of that as well. Now, we can look at how the voltage and the current and the resistance all work together to make things in the modern world work for us. But we're typically going to look at those in terms of what's known as a circuit diagram. Okay, and a circuit diagram, we need some symbols that we can be using here to make sure that that we can show how these things work. I'm going to show you some examples of these in a second, but I want to show you some of the most basic circuit diagram symbols. And you see some of those on the right there. These are specific symbols that represent different parts of a circuit. So when we actually want to draw a schematic to show where different pieces of a circuit are for, let's say, your computer, right? You can't just like put this together without having some sort of schematic that shows how it works. Same for your phone or all these different electrical devices, or quite frankly, the layout of electricity within the building that you're in right now. Okay, so we need to be able to represent these in some way. The most common ones that we're going to use in this class are just going to be the resistor. So you see that right here, this little squiggly line guy right here. A cell, so a battery is what that is, a cell or a battery. Either one of these would be considered the voltage source. And then a wire, and a wire is just a straight line. Like you see a wire going into and then coming out of this representation of an ammeter. That's basically it. So those are the three symbols we're going to use the most. If we end up using anything else, we'll make sure to point that out along the way here. But note those three because you're going to be expected to know those three. Those are not on an equation sheet or anything, but we'll use them enough that you'll get very used to them. So to actually look at what a circuit diagram might look like here, all right? We have the visual representation of a circuit. That's what this is meant to be. So you see a drawing of a circuit on the left. And this is, okay, we got a little battery pack. It's got 3 batteries in it. You see the little wires that connect it all to make sure that it will work. We've got 3 different light bulbs that are all together here. So we've got, I don't know, some little LED light setup that's battery powered, and that's what's going on. Okay, so that's what we're actually looking at would be here. The circuit diagram is here. And we see how those match up, hopefully, pretty quickly. We've got the 3 long lines and 3 short lines representing the 3 batteries. We have our little squiggly lines here representing the resistors, which in this case are just light bulbs. And we have the wires all represented by straight lines here as well. Now, this doesn't look much different, right? But if you're going from 3 basic batteries and 3 basic light bulbs to something like all of the crazy different pieces that go into making a computer in a very small space, you've got to have some sort of diagram that can represent that as opposed to trying to draw all those different things. All right, that's why we do this. And it follows flow of electricity to help solve for these different problems. Now, there are 2 very basic types of circuits, and then there is different ways to combine those different types of circuits. So we're going to start with what's known as a series circuit. Okay? Series circuit is really the most basic thing that we've got going on when we have current traveling. This is a circuit through which electricity has one path to follow. So we have a battery here. Okay? And typically we consider an electrical flow to go from out of positive and then around the circuit and into the negative. All right? So out of the positive, up here, over through the circuit, so through each light bulb, and then back into the negative. Because there's only one way for this electricity to travel at any point, we would call this a series circuit, which is to say that all of these things are in series or are in a row with each other. So the current has one path to follow. If we open the switch here, or if you were to turn the switch for the lights on the wall of your room or anything else that has a switch to it, you're going to make it so that the current can't flow because there's going to be a spot. It can't keep going in that circle. It has to move in this circular pattern, and it's not going to work. You turned it off. That's why we have switches, right? So from there, the resistance, and we're going to talk about how you could calculate these different pieces of this, okay? The resistance in a series circuit is just going to be the sum of each of the resistors in it, okay? So if each one of these had a resistance of 10 ohms, then the total resistance for this circuit would be 10, 20, 30 ohms. Boom, done. Okay? Now the voltage for this is going to be the sum of the batteries. So if we look back here, the voltage total here would be, I mean, if they're 9-volt batteries, 9, 18, 27, 27 volts. That's the total voltage that would be there. Now the voltage drop is what pushes the current through a resistor. And this is probably the toughest part of this, okay? So the voltage drop is what pushes the current. Well, when you have a resistor, it doesn't want, it's a resistor, it's resisting the current. So it's going to be harder to push the current through a resistor than it is for the current to just move through the wire that's set up for it to move through easily. Okay? So you're going to have what's known as a voltage drop at each resistor, which means some of that total voltage is going to be used up. So let's say again, we have 27 volts here total in the battery. Well, if these are all the same, which we said they were, then it's going to take 27 volts here. It's going to take a third of that, 9 volts, to push through this resistor. So we have 18 left here. Another third, 9 more volts to push through this resistor. So we'd have 9 volts left there. And then the last third to push through this resistor. So we'd be down to 0 volts. The current would still be flowing, but it's not going to get pushed through anything else at that point. And that's good because we're at the end. So it would come back here. We'll go back to the battery source. It would get a new push and it would go through again. And this happens continuously. And that's how electricity works. Okay. So the next one right here is a parallel circuit. A parallel circuit is a circuit in which there is more than one path for electricity to flow. It could be 2, it could be 1,000,000, honestly, right? It's just more than one. So if we look here, we have our battery right here and electricity flowing out of it. And it flows to here, and there's 2 options. Either it goes through this resistor or it continues on to this resistor. Some is going to go through here. Some is going to go through there. It's going to be based on the push of all of it to this point. And then so it's going to take basically the path of least resistance. Some is going to move through here, but eventually it's going to be hard to move through this resistor because it's resisting the current. And so some of it's going to then move down through this branch and then it can get pushed through this. They're going to come back together right there and then move back to the battery. Okay? So the total voltage is going to be the sum of however many batteries we've got. The voltage drop is going to be the same through all of them. And this one's interesting. And this makes parallel circuits much more efficient overall when we are making circuits on a larger scale. But that means the push that's here, it's going to get to this point, and whatever push there was leading to it is going to push some through that and some through this. And so the voltage drop across both of those will be the same. Now we'll do a bunch of labs where you'll see this, specifically some simulations that really show this because they give little representations of the current as it moves. And so you'll see a lot more of this going forward. I realize it's probably a little confusing now if you're hearing it for the first time, but we will do a lot more with this. All right. Now the resistance, another thing, and the reason that these are so efficient here is because we have to sum the reciprocals of the resistors in order to determine the total resistance here. So the total resistance of, let's say, this circuit where we have 1, 2, 3. This could be our 3 light bulbs from earlier, okay? The total resistance of this, the 1 over that, the reciprocal of the total resistance will equal 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3 until we get through all of the resistors that are there, okay? So to find that total resistance, we're going to add the reciprocals all together, and that means that the total resistance in a parallel circuit will always be less than the lowest resistor. So whichever one of these is the smallest, this will be less than that. And so we can get a lot of oomph for our current, that's a weird saying, but whatever, out of what we're seeing here, okay? And y'all, we're getting close to the end. We're just going to look at some specifics for these different circuits. It's coming up here. All right, so the current in something like this is going to break up through these different paths, as we talked about, right? So the total current here for in A1, it's coming out here. We've got our current. The total current's going to be there. Well, then some's going to break up and go this way, some that way, some this way. But if I add whatever's going through 2 and through 3 and through 4 together, I'm going to get the current. And now we're going to start thinking about this, as we would with a lot of currents, as if it was water flowing. If I put a bunch of water flowing down this path, well, if some of it branches off here, and some of the water branches off there, and some of the water branches off here, but all those branches come back together, then before it gets back to the battery, I'm going to have my total current again, okay? So just think of it a lot like current is really capable of thinking about current like it's water, All right, however much is flowing through one branch plus the other is going to come back together to be the total. If you're in a series circuit, it's going to be the same at every location because there's one path. So it's one river, no branches, it's all flowing through that one path in that case. All right. We see a couple examples here. We've got nine amps here, but 3 go this way, 3 go that way, 3 go this way. And so there's 3 at the end of each here, but it would come back together to be 9 up there. So we see, I think, what's a better representation right here. 0.3 amps, well, we have different currents running through each branch here, but they all come back together to be 0.3 amps. And same thing here, 0.3 and 0.3, but now they're all the same. And this could be the case because all 3 of these resistors would be the same type thing. This could be like our 3 light bulbs. Whereas here, we might have, let's say, this one would be the most, so a computer plugged in there, a small TV here, and maybe just a little fan there would be 3 things that could be plugged in. And so they would each draw a different current, but again, it would come back together to be the total. It's not disappearing. All right, now I'm going to kind of quickly go through what happens when we have these different types and they work together, because we're going to do a lot of this in class and in person, because when you see us combining these types of circuits, it gets a bit more in depth, and you'll need some practice with the basic circuits first. But when we combine types of circuits, we put these series and parallel together. That's going to be the way it really is. You're very rarely going to see just a series or just a parallel circuit. Okay, they work together in almost every case. The rare example for just one would be like a string of Christmas lights, right? That used to be in series, but now they make them in parallel because it used to be then if one light bulb went out, the whole string went out. Now one light bulb can go out and the string still works because they're in parallel. All right, so we had our series here. We take all of our resistances, we put them together to make that. We had our parallel here. We take each of these and we sum the reciprocals to find, right, what we've got going on there at the end. And here's a quick, and this is probably helpful and probably something worth saving somewhere, a quick setup of all the rules so that you can find them all together, okay? So this is your current. It's the same in each location for series circuits, okay? The resistance, the total resistance is going to be the sum of all the resistances. Now the total voltage is going to be the voltage drop at each location added together. So if it took 9 volts to get through one and 9 through the other and 9 through the other, we used all of our voltage, and that meant we had 27 volts total, like we talked about earlier. And then in parallel, our rules are, okay, now the current here, it's not the same, right? Here in series, it was the same everywhere. Here in parallel, it's the sum of those currents through each of the branches. And we looked at that, right? And voltage here is the same through each of those branches, okay? And that's because that pushes the whole system. And then again, the resistance is the reciprocal all the way through. So we've looked at all those, but a quick summation. This is actually given on the North Carolina curriculum. These rules are given to you honors physics students on their equation sheet. They are not for AP physics, but that's where I pulled these right off of the honors physics equation sheet. So it's worth noting and maybe even worth saving these slides somewhere to make sure that you have them to reference. All right, so I'm going to walk through one quick example here so we see how we can simplify some of these. So what we've got here is what we would call a series parallel circuit. Now, whenever you see a circuit, just a general rule, we're going to solve in the order of the way the resistors are labeled. And that's just how we're going to do it. We're going to follow that. So I see 1 and 2 here, and then 3 there, okay? What I would do then is I see that 1 and 2 are in parallel, right? Because there's more than one way for the electricity to flow. But then those together, if we combine them, would be in series with 3. So I would combine this using my parallel rules. And then once that's together, I would use that combined with 3 in my series rules. Okay. And so we can kind of see how all that would work together here. But this one actually breaks it down step by step. So this is what we're going to look at here. Now, I don't expect you to be able to do the math for these yet. We will build up to that as we move through this unit. But what we've got 1 and 2, they're in parallel. And they're the only 2 in parallel with each other. So we're going to combine those to form what we're going to call R12. Now they're combined. Now if I look here, I have 1, 2, these 2 separately in series. So I'm going to combine them to be 1, 2, and that's 4. So this is now 1, 2, 4. Well, now if I look right here, 1, 2, 4, so these that were together over there are in parallel with 3. So I would use my parallel rules to combine that to find my total resistance. So again, right here, these are parallel, and they're the only 2 in parallel. So I'm going to combine those to be this. These are in series, so I'm going to combine those to be this. And now these are in parallel. I'm going to combine those to find my total. And then we're down to have simplified this as far as we can. All right, so to look again at what we could refer to here, these are series parallel and series parallel circuits. They're the three main types. And we see the connection points, a reminder there, series circuit, there's one shared connection point between components. That means they're all in one line together. And then the parallel has two shared connection points. It means there's more than one path for the electricity to flow. And so we could see different names for some of these here, right? But series, we see those together. The parallel, all those in parallel with each other. This is one way we could see a series parallel. So we have these two in parallel with each other that are then in series with something else. Or we could see this way that is also a series parallel circuit where these two are in series with each other and they're in parallel with this one over here. All right, we're going to get a lot more into that as we go through the class, so keep that in mind, please. And now we're back to our big ideas. And so a reminder real quick, we're seeing charge as it's flowing here. We're seeing the fields and the the electrostatic fields that can surround a charged object. We see interactions of these as these objects are transferring charge or have a current flowing through them. We see changes in the systems potentially in our different ways of transferring charge, and changes that occur are a result of these conservation laws. Remember, these charges are not being created or destroyed, they're just being transferred from one spot to the other. So I hope that's helpful, get you into a good intro for electricity. We'll do a lot more with it for the class. Thanks for being here.